Hello students, how are you all? Welcome to the third session of real numbers. I'm Kanika ma'am, your mathematics teacher. So we just had two sessions of real numbers, and where we had started the basics of real numbers, we had started the Euclid's division lemma, and we have also discussed a few questions of NCERT. We have discussed Euclid's division algorithm also, and in yesterday's class we had discussed in detail fundamental theorem of arithmetic. I hope you've all practiced the same and you've understood the concepts well. Okay, so now today is very important class. Today we'll be doing something very different. As I just told you in the first class, that square root of all the prime numbers, they are irrationals. Today we'll be proving the same. So before we begin with, we'll just quickly revise what we did in the last two classes. Now, real numbers, those numbers which include both rational and irrational numbers. Rational numbers are those numbers which can be written in P by Q form, and irrational numbers are those numbers which cannot be written in P by Q form. So together, when we combine rational and irrational numbers, they are real numbers. Euclid's division lemma also we studied in the previous class. Given two positive integers a and b, there exist unique positive integers q and r, satisfying a equal to bq plus r, where 0 less than equal to r less than b. Now this lemma we were applying repeatedly to solve for the HCF of given numbers. So that's Euclid's division algorithm. We had learned Euclid's division algorithm to solve HCF of two numbers. So children, there is a good news for you that the Euclid's division lemma, it is not there in the syllabus of CBSE in the coming session. Though we have discussed the same, but that's okay. I have discussed the same with you because in future, if you will sit for any competitive exam, you might come across some question related to the same. That is why I've discussed the same. Now, also, we had discussed fundamental theorem of arithmetic in the previous class, which says every composite number can be expressed or factorized as product of primes, and this factorization is unique apart from the order in which the prime factors occur. So based on this fundamental theorem of arithmetic, we had discussed a few questions of NCERT where we were expressing some numbers as product of prime factors. Also, we have started an important concept that HCF of two numbers, if we take and we take LCM of those two numbers and we multiply them, so the result would be same as product of the numbers. This also we discussed yesterday, and we had done one question based on the same. And we also discussed yesterday the questions like this: check whether 6 raised to the power n can end with digit 0 for any natural number n. So this we discussed yesterday also, but still I am discussing this again with you all since this is very important, and this can come in different forms. Check whether 6 raised to the power n can end with digit 0. For any number to end with digit 0, that means to have 0 in the ones place, we should have 10 as the factor of that number. So if 10 is a factor of a particular number, then 2 and 5 will also be factors of that number. So 6 raised to the power n, to have 0 in the ones place, must have 10 as a factor. We can also say must have 2 and 5 both as the factors. Now I'm going to write this 6 as 2 into 3. So now this becomes 2 into 3 raised to the power n. That is 2 raised n into 3 raised n. Now children, from here we can see that 2 is a factor of 6. 3 is also a factor of 6. But for 6 raised to the power n to end with digit 0, we should have 2 and 5 both as a factor of 6 raised n. But here we have 2, but then we don't have 5. 5 is missing here. So we can say 6 raised to the power n cannot end with digit 0. It cannot end with digit 0. So this we had discussed yesterday also. Now we'll continue with the same exercise, which where we had LCM and HCF concepts. So this question I've taken from NCERT. There is a circular path around a sports field. Sonia takes 18 minutes to drive one round of the field, while Ravi takes 12 minutes for the same. Suppose they both start at the same point and at the same time and go in the same direction. For after how many minutes will they meet again at the starting point? Now children, such questions you might have come across in grade 6 also in Playing with Numbers chapter, if you remember, where at that time a lot of students used to face that difficulty whether to find the HCF or LCM. In this particular question, we are going to solve for the LCM, because please notice, just try to understand the question. It is very logical that we have two people, Sonia and Ravi. They're taking round along a circular path in a sports field, and Sonia takes 18 minutes to take one round. Ravi takes 12 minutes for the same. That means to take the same round, he takes 12 minutes. Now, after how much time they're going to meet again at the starting point? So something which is happening simultaneously. In this case, we'll solve for the LCM of 18 and 12. So 18 and 12, if we solve for the LCM, this will go by 2. We'll get 9 here. Then we'll get 6 here. The 6 will be divided by 2. I cannot divide 9 by 2, so I'll write it as it is. And this is 3. And 9 and 3, they're both divisible by 3. So we'll write here 3 and then 1. 3 again, 1 and 1. So now LCM of 18 and 12, we have 2 into 2 into 3 into 3, that is 36. So LCM of 18 and 12 is 36. That means after 36 minutes, Sonia and Ravi will again meet at the starting point. I hope you've all understood this. Okay. Now, as I just told you right in the first class, the square root of all the prime numbers, they are irrational. So today we'll be focusing on that particular concept. We'll be proving the same. Before we prove that, I am going to discuss this theorem with you. Only the statement of this theorem is required. Proof is not there in your syllabus. So if you have your NCERT, I'll just tell you, it's given on page number 12, theorem 1.3. Let P be a prime number. If P divides A square, then P divides A, where A is a positive integer. I'm repeating this. Let P be a prime number. If P divides A square, then P divides A, where A is a positive integer. So let us take a prime number. Let's take 2. 2 is a prime number. That is what we are taking. If P divides A square, so let us say that 2 divides 10 square. 10 square is 100. We know that 2 divides 100. 100 is completely divisible by 2. We know this. So if 2 divides 10 square, that is 100 actually, then can we say that 2 divides 10 also? Yes, 2 divides 10 also. 10 is divisible by 2. So let P be a prime number. If P divides A square, then P divides A, where A is a positive integer. So this holds for any positive integer and for any prime number P. So if 2 divides 10 square, then 2 divides 10 also. Now students, will be using this concept in the theorem which we'll be proving further. Now, square root of 2 is an irrational number. This we have started in grade 9. Square root of 3 is an irrational number. Square root of 5 is an irrational number. In fact, square root of all the prime numbers, they are irrationals. So we'll be proving the same. We'll start with square root of 2. Square root of 2 is irrational. So when we come across such questions, we go by contradiction method. Contradiction method means that we'll assume something contrary to this, and we'll arrive at something which will be totally wrong. I'll show you how, since this is the first time. I'll do it for you. Theorem root 2 is irrational. We'll start with, let, if possible, root 2 be a rational number. So we have been asked to prove that root 2 is irrational, but then we have taken root 2 as a rational number. Just see what happens after this. Now, if root 2 is a rational number, we can write root 2 as A upon B, where A and B are co-prime. Co-prime concept you have started in grade 6 also. Co-prime means that the HCF of A and B is 1. There's no common factor of A and B other than 1. We can say that root 2 is equal to A by B. We have written A by B in the simplest form, in the standard form. Also, B is not equal to 0. B cannot be 0 since B is in the denominator. Root 2 is equal to a and b, where a and b are co-prime. Children, this is very, very important because we'll arrive at the contradiction using this statement only. Do not forget to write the statement. Now in the next step, we'll take this b on the other side and we'll multiply. So we will get b root 2 is equal to a. In the next step, we are going to square both the sides. So we'll get b root 2 square equal to a square. Then we will get b square into 2 equal to a square. After this, we'll take this 2 on the other side and this will get divided. So we'll get b square is equal to a square upon 2. This is what we're going to get. Also, I'm naming this as equation 1 since I'll be using this in the next step. Now, b square is an integer. A square upon 2 we are dividing a square by 2 and we are getting an integer. That means we can say that a square is divisible by 2, or say 2 divides a square. So we can say here 2 divides a square. Now if 2 divides a square, 2 is a prime number. We've just discussed that if a prime number p divides a square, then p divides a also. So in the same way, if we have a prime number 2, it divides a square, then 2 divides a also. Now if 2 divides a, we can write a as 2 times of c for some integer c. I'm repeating this. If 2 divides a, then a is equal to 2c for some integer c. Now we are going to square both the sides. So we'll get a square is equal to 2c square. Then this will be a square is equal to 4c square. Now this I'm naming as second equation. Now please observe the first equation where we have b square into 2 equal to a square. And this says that a square is equal to 4c square. So I can then equate this and this because they're both equal to the same thing. They're both equal to a square. They're both equal to a square. So in the next step, I can write equation 1 and 2 implies 2b square is equal to 4c square. Now we can cancel out this 2 and 4. This will go 1 time. This will go 2 times. So we'll get b square is equal to 2c square. Now in the next step, I'm going to take 2 on the other side and this will get divided. So we'll get b square upon 2 is equal to c square. Here it's the same thing. We are taking b square, we are dividing by 2, so we are getting an integer. So we can say that b square is divisible by 2. We can also say 2 divides b square. So we can say here 2 divides b square. 2 is a prime number, it divides b square, so we can say 2 divides b also. So we are using this theorem. If p divides a square, then p divides a. So if 2 divides b square, then 2 divides b. Now please observe 2 divides b we have written here. Also we have written 2 divides a. So can I say that 2 is a common factor of a and b? Yes, we can say that. So 2 is a common factor of a and b. But right in the beginning, we said that root 2 is equal to a upon b, where a and b are co-prime numbers. That means they don't have any other common factor other than 1. They just have 1 as the common factor, nothing else except that. But now we are saying 2 is a common factor of a and b. So that's a contradiction. That's a contradiction. So this is wrong. It's a contradiction. That means our assumption was wrong. That means right in the beginning when we said let if possible root 2 be a rational number, that's a completely wrong statement. So we'll write therefore our assumption was wrong. Our assumption was wrong. Thus our assumption was that root 2 is a rational number. That's a wrong thing. So if it's not rational, it has to be irrational. Thus, root 2 is an irrational number. So, children, this is something very, very important. I'm repeating the entire proof for you. Let's start again. Root 2 is irrational. We have to prove that. We are going to start it like this. Let, if possible, root 2 be a rational number. So if root 2 is a rational number, it can be written as a upon b, where a and b are co-prime numbers. That means a and b, they don't have any common factor except 1. And b is also not equal to 0. B is non-zero because b is there in the denominator. In the next step, we'll take b on the other side and we'll divide by root 2. So we'll get b, we'll multiply by root 2. So we'll get b root 2 is equal to a. Now we are going to take squares on both the sides. So we'll get b root 2 square equal to a square. This b square we are going to write here, and root 2 square will become 2. A square I've copied as it is. In the next step, we've taken 2 on the other side. Now this is b square equal to a square upon 2. And this means that 2 divides a square. 2 divides a square because a square, we are dividing by 2 and we are getting an integer. So 2 divides a square. If 2 being a prime number divides a square, then 2 divides a also. Now a is divisible by 2. 2 divides a, or a is divisible by 2 is the same thing. So we can write a as 2c for some integer c. In the next step, we are going to square both the sides. So we'll get a square equal to 2c whole square. Now this 2 square will become 4, c square we've written here. Now please observe, a square is equal to 4c square. Also, a square equal to 2b square. So we are going to equate this 2b square and 4c square since they are both equal to a square. So we have 2b square equal to 4c square. We can cancel out this 2 and 4. So we'll get b square equal to 2c square. 2 we are going to take on the other side and it will get divided. Now we are getting b square upon 2 equal to c square. B square upon 2 equal to c square we are getting. This means 2 divides b square, and 2 being a prime number, if it divides b square, it is going to divide b also. Now 2 divides b, 2 divides a. So we can say 2 is a common factor of both a and b. 2 is a common factor of both a and b. But right in the beginning, we said a and b are co-prime numbers. They don't have any other common factor except 1. But here we are saying that 2 is a common factor of a and b. So that's a contradiction. So our assumption was wrong. Our assumption right in the beginning was that root 2 is a rational number. So that's a wrong statement. Thus, we can conclude that root 2 is an irrational number. Children, I hope you have all understood this. And the same proof holds for square root of all the prime numbers. The same thing holds for square root of 3, square root of 5, square root of 7. So you can just follow similar steps. You can do the proofs on the same lines for square root of all the prime numbers. So in the exam, you can be asked to prove root 3 is irrational, root 5 is irrational, root 7 is irrational, like this. So at home, please do this. Root 2 is irrational. Practice this. Also practice the same for root 3 also and root 5. Root 5 is irrational. That's one of the questions of NCERT. Try to do this on your own. It's on the same lines. Now, in NCERT, there's an exercise based on the same concept here. Prove that 3 plus 2 root 5 is irrational. Now, root 5 we know it's irrational because it's square root of a prime number. You can prove it using the same proof which I just gave you for root 2. Now, when such questions come in the exam, prove that 3 plus 2 root 5 is irrational. We'll do it as we did this root 2 theorem. Let 3 plus 2 root 5 be rational. We are assuming this to be a rational number. Now, 3 plus 2 root 5 is a rational number. So, we can write 3 plus 2 root 5 is equal to a upon b, where b is non-zero. And then you can take a and b as co-prime. So if I'm taking a, b like this as an ordered pair in bracket and then I'm writing equal to 1, this means common factor of a and b is only 1. A and b are co-prime numbers. So we can write this symbolically. Now, one at a time, we are going to take all the terms on the left hand side and we'll take it to the right hand side. I'll show you how. This 3, I'm going to take it here. So we'll get 2 root 5 is equal to a upon b minus 3. So 3, when it is going to go on the other side, it will become minus 3. Then we have 2 root 5 is equal to a minus 3b upon b. So I've taken LCM here. In the next step, 2 I am going to take here, it will come in the denominator. So we will get root 5 is equal to a minus 3b upon 2b. Now students, please observe this root 5 we have written in the form of p upon q. So we can say that this is a rational number. So I'll just write it here. A minus 3b upon 2b is rational. Now children, if this is rational, we can say that root 5 is also rational because that's equal to root 5. So we can say that root 5 is rational. But that's a contradiction. We know that square root of all the prime numbers, they are irrational numbers. So that's a contradiction. So our assumption was wrong. That means right in the beginning, if we said that 3 plus 2 root 5 is a rational number, that's a wrong statement. So we can conclude 3 plus 2 root 5 is irrational. I hope you've all understood this. We'll do some more questions also of similar type. Or if you want, I'll just explain it again. Since you're very new to this concept. So I'll explain it again. Let 3 plus 2 root 5 be a rational number. We have been asked to prove that it's an irrational number. We start with let, if possible, 3 plus 2 root 5 be a rational number. Now, if this is a rational number, we'll write it in the form of a upon b, where b being a denominator is non-zero. And a and b, they're co-prime numbers. That means they have only one as a common factor. 3 we are going to take on the other side. It will become minus 3. So the purpose here is to take one term at a time from the left hand side and take it to the right hand side. We should be left with only square root of 5 on the left hand side. So we have a upon b minus 3. Here we are going to take the LCM. We'll get a minus 3b upon b. 2 we'll take on the other side. This will go in the denominator and we'll get a minus 3b upon 2b. This is of the form of p by q. So we can say a minus 3b upon 2b is a rational number. Now, if this is a rational number, we can say root 5 is also a rational number since they are equal. So we have root 5 is a rational number. That's a contradiction. It's a contradiction because we know square root of all the prime numbers are irrationals. Finally, we can say that our assumption 3 plus 2 root 5 is a rational number was wrong. So we can conclude 3 plus 2 root 5 is irrational. Now children, on the same lines, we'll prove the next one. In fact, this is very simple. Prove that the following are irrationals. So we'll start with 1 upon root 2. So we'll start in the same way. Let, if possible, 1 upon root 2 be a rational number. Now, if this is a rational number, we can write 1 upon root 2 in the form of a upon b, where b is non-zero, and we can say a and b are co-prime numbers. Now, root 2 is here in the denominator. We are going to take the reciprocal of both left and the right hand sides. So, if I reciprocate both of them, I'll get root 2 upon 1 is equal to a upon b. I can just write it as root 2 is equal to a upon b also. It's the same thing. Now, root 2 is in the form of a upon b. So, we can say that a upon b as I can say, see here, that it's a rational number. So, a upon b is rational. Now, if this is equal to root 2, then we can say that root 2 is also rational. So, that's a contradiction. Root 2 is rational, that's a contradiction. It's a contradiction because we've just proved that root 2 is an irrational number. Finally, we can say that our assumption was wrong. 1 upon root 2 is an irrational number. 1 upon root 2 is an irrational number. Now, in the same way, we'll do the next part, 7 root 5. So, we have to prove that this is an irrational number. We start in the same way. Let, if possible, 7 root 2 5 be a rational number. Now, if 7 root 5 is a rational number, we can say that 7 root 5 can be written in the form of a upon b, where b is non-zero and a and b, they are co-prime numbers. In the next step, we'll take 7 on the other side. So, we'll get root 5 is equal to a upon 7b. Now, this is of the form p upon q. So, we can say that this is a rational number. A upon 7b, we can see that it's a rational number. is a rational number. So if this is rational, then this is also rational because they're equal. So we can say root 5 is rational. Again, this is a contradiction. It's a contradiction because we have just proved that square root of all the prime numbers, they are irrational. So our assumption was wrong. This was our assumption. It's wrong. So we can say 7 root 5 is irrational. That's quite simple. In the same way, we'll do the next one also. We want to prove 6 plus root 2 is irrational. Let, if possible, 6 plus root 2 be a rational number. Now, if 6 plus root 2 is a rational number, we can write it in the form of a upon b, where b is not equal to 0 and a and b are co-prime numbers. So, as I told you earlier, we are going to take each term of the left hand side and one by one take it to the right hand side. Only root 2 will remain here. So I'm going to take the 6 on the other side. I'll get root 2 is equal to a upon b minus 6. Now we are going to take the LCM here. We'll get a minus 6b over b. So this is in the form of p by q. So we can say a minus 6b over b is rational. Since this is equal to root 2, we can say that root 2 is also a rational number. So we can say root 2 is a rational number. So root 2 is a rational number. It's a contradiction because we've just proved that root 2 is an irrational number. Thus our assumption was wrong. 6 plus 2 root 5 be a rational number. This statement which we just said, it's a wrong statement. Finally, we can conclude 6 plus root 2 is an irrational number. Children, I hope you've understood all this. Okay. Now, let us proceed further to the next concept. That's very, very simple. That's related to grade 9. Now, you've studied rationals and irrational numbers in grade 9. And you've also studied about their decimal expansion. We know for every number, the decimal expansion is either terminating or non-terminating. So, if the decimal expansion is terminating, we say that it's a rational number. I hope you all remember this. You've studied in grade 9 also. So, for a decimal expansion, if it's terminating means it's ending. It is ending somewhere. Then we say that it's a rational number. If the decimal expansion is non-terminating, it is not ending, but it is repeating. After some time, the digits are repeating themselves, then also it is a rational number. So just see the decimal expansion where it is non-terminating and repeating. It's non-terminating, that means it's not ending, it is going on forever. It is repeating, that means after a certain stage, the digits are repeating themselves, then also it is a rational number. So for the decimal expansion having terminating decimal expansion, we can say that the numbers are rational. For non-terminating repeating decimal expansion, we can say that they are rational numbers again. But for non-terminating, non-repeating decimal expansions, they are irrational numbers. They are irrational numbers. Non-terminating, non-repeating means the decimal expansion is not ending. It is not even repeating. That means after a certain stage, the digits, they are not repeating themselves. We are randomly getting the digits here. So non-terminating, non-repeating decimal expansion is a rational number. Terminating decimal expansion, non-terminating, non-repeating is an irrational number. Terminating decimal expansion will give us rational number. Non-terminating repeating decimal expansion will give us rational number. Now please notice that we have a rational number in case of terminating decimal expansion and in case of non-terminating repeating decimal expansion. Now if we have a rational number, it's written in P by Q form, we know. How will we figure out whether the decimal expansion is terminating or non-terminating repeating? So we are going to understand this concept in detail. So just all this, whatever I've explained you, this flowchart, I'll just quickly read out this. A terminating decimal is a decimal that has an end digit. It ends somewhere it is a decimal which has finite number of digits or terms. So the digits, they are ending somewhere, so we have finite number of digits in it. Non-terminating decimals are the ones that does not have an end term. They go on forever and it has an infinite number of terms. Now, terminating decimals are those numbers which come to an end after few repetitions after decimal point. So after some time they end somewhere. Like I've given examples here. We have 0.5, 2.456, 123.456, like this. We have terminating decimals. Non-terminating decimals are those which keep on continuing after the decimal point. So as I just explained, non-terminating, we have two types. Non-terminating repeating. That means after a certain stage, the digits, they are going to repeat themselves. And then we have non-terminating, non-repeating. That means the digits, they don't repeat themselves. You will randomly keep getting the digits and they will go on forever. So non-terminating, non-repeating, they are irrational numbers. Non-terminating, repeating, they are rational numbers. Now we have a theorem based on the same. Let x equal to p by q be a rational number such that the prime factorization of q is of the form 2 raised n, 5 raised m, where n, m are non-negative integers, then x has a decimal expansion which terminates. Now this theorem means that if we have a rational number, it's written in p by q form, then if we take q, I'm talking about the denominator here, q, and we prime factorize the same. And the prime factors, they're of the form 2 raised n, 5 raised m, where n and m are non-negative integers. This means if we take q, that's the denominator, and we prime factorize the same, we get the prime factors as 2 or 5 or both. We must get 2 or 5 or both and nothing else except that. We should not get any other prime number like 3, 7, 17, something like that, nothing. We should get either 2 or 5 or both. If we are getting like this, then we can conclude that x has a decimal expansion which terminates. Then the decimal expansion of that particular rational number will terminate. I'm repeating the entire thing again. If we have a rational number, it's written in p by q form, and we take this q, that's the denominator, and we prime factorize the same. If we get the prime factors in the form of 2 raised n, 5 raised m, where n and m are non-negative integers. This means that if we get the prime factors of q as 2 or 5 or both and nothing else except that, then we can say that x has a decimal expansion which terminates. It ends somewhere. For example, we have 13 upon 3125. If I prime factorize this 3125, I'm going to get 5 into 5 into 5 into 5 into 5. So I'm going to get this. And then the decimal expansion of 13 upon 3125 is it is terminating. It is terminating. Sorry, it is terminating. It's not non-terminating. It is terminating. It is terminating because here we are getting the prime factors only as 5. So as I just told you, it should have either 2 or 5 or both. Nothing else except that. So this is the case of terminating decimal expansion. Now coming to the next theorem. If we have x as p by q, it's again a rational number, such that the prime factors of q is not of the form 2 raised n, 5 raised m, then n and m are non-negative integers. Where n and m are non-negative integers, then x has a decimal expansion which is non-terminating repeating. So here we have x, a rational number. It's written in p by q form. And here q, that's the denominator, is not of the form 2 raised n, 5 raised m. That means we are getting the prime, if we take the prime factorization of q and we have the prime factors as 2 or 5, even both we are having, but then we are having something other than 2 or 5. So if something else other than 2 and 5 occur, even if 2 and 5 are occurring or not, that doesn't matter. Something else other than 2 and 5 they occur, like we get 3 or 7 or 11 or 13, some other prime factor we get. Then we can say that the decimal expansion is non-terminating repeating. Like in this case, we have 64 upon 455. We have written this 455 as 5 into 7 into 13. Then the decimal expansion of 64 upon 455 is non-terminating repeating, because we are getting 5, but then we are getting 7 and 13 also. That is why we will say that 64 upon 455 is non-terminating repeating. All right, children. Now, based on the same concept here, we have some questions on page number 17. I'm discussing the same with you all. So the question here, first question of exercise 1.2. Without actually performing the long division, state whether the following rational numbers will have a terminating decimal expansion or a non-terminating repeating decimal expansion. So this one is very simple. The first part is 17 upon 8 we have. We just have to prime factorize the denominator, that's all. So we can just do it orally. 8 can be written as 2 into 2 into 2, like this. Then we have the prime factors of 8 as 2. So I just told you right in the beginning, for a rational number to have terminating decimal expansion, it should have the prime factors either 2 or 5 or both or nothing else except that, nothing else apart from 2 and 5. So in this case we are just getting 2, so we can say that this 17 upon 8 has terminating decimal expansion. Terminating decimal expansion. Now let's try the next one. I think this we've already discussed. 64 upon 455. Here I have discussed in the form of example. We have 5 into 7 into 13. These are the prime factors of 455. So this is not of the form 2 raised n, 5 raised n. As we are getting 5, but then we are getting prime factors other than 5 and 2. Then we have 7 and 13 here. So we'll say 64 upon 405 has non-terminating repeating decimal expansion. Now let's talk about 15 upon 1600. So we'll just prime factorize this 1600. We'll start with 2. We'll get 800 here. So this prime factorization we have discussed in detail yesterday also. Then 2, we'll get 400 here. Then we'll divide by 2, we'll get 200. We'll divide by 2 again, we'll get 100. We'll divide by 2, we'll get 20. We'll get 50 here. Then we are going to divide by 2, we'll get here 25. Then by 5, 5 again, and then by 5. So please observe here the prime factors of 1600. We are getting 2's and 5's and nothing else except that. So we can write this 15 upon 1600 as 15 upon 1, 2, 3, 4, 5, 6. 6 times. 2 raised 6 into 5 square. So we are getting in the form of 2 raised n, 5 raised m. So we can say that it has terminating decimal expansion. So the decimal expansion here is terminating. Now let's observe this one. So this one is already done for you. You don't need to prime factorize this. Just observe that the denominator is of the form 2 raised n, 5 raised m. And we can observe here 2 raised n, 5 raised m we have. We can observe this is of the form 2 raised n, 5 raised m. We have 2 and 5 both, but nothing else except that. So this is the case of terminating decimal expansion. Now let's discuss this one. We have 29 upon 343. 343 we know it's a cube of 7. So we can straight away write this as 7 cube. So this denominator, the prime factorization of the denominator is not of the form 2 raised n, 5 raised n. Apart from 2 and 5, we have 7 here. In fact, 2 and 5 we don't even have. So this is the case of non-terminating repeating decimal expansion. Now the next one, we have 2, we have 5, but then we have 7 also here. So this is again of the form non-terminating repeating decimal expansion. Now let's discuss this one, 6 upon 15. So 6 upon 15, before we do anything else, we can simplify this. We can write this as, let's divide both numerator and denominator by 3. We'll get 2 and we'll get 5 here. So that's 2 upon 5. In the denominator, we are just getting 5. So this is the case of terminating decimal expansion. Now the next one, 35 upon 50. 35 upon 50, we can simplify this first. We'll divide both numerator and denominator by 5. We'll get 7 here and then we'll get 10 here. So this is 7 over 10, and then this 10 we can write it as 2 into 5. So this is of the form 2 raised n, 5 raised m. the prime factors of 10, that's the denominator. We have 2 and 5 both, nothing else except that. So it's the case of non-terminating repeating decimal expansion. 77 upon 210. Now let's solve this one. So in this case also, as we can see that this is divisible by 7. Both numerator and denominator, they're divisible by 7. This will go 11 times and this is going to go 30 times. So we have 11 upon 30. We can prime factorize this 30. We can write this as 2 into 5 into 3. So the prime factors of the denominator here, we have 2 and 5 both, but then we have 3 also here. So that's the case of non-terminating repeating decimal expansion. Okay. All right, children. So we are done with the entire chapter here. So I'll just quickly summarize what we have discussed in the last 3 sessions. So in this topic, we have started Euclid's division lemma, and we've also used the same to find the HCF of two numbers using Euclid's division algorithm. We've also started in detail fundamental theorem of arithmetic, where we say that every composite number can be written as product of the prime numbers. The prime numbers which we write, they're unique apart from the orders in which they occur. You can rearrange the prime factors, but then you cannot change the prime factors. Rationals and irrational numbers also we have studied in detail. Rational numbers are those numbers which can be written in P by Q form. Irrational numbers are those numbers which cannot be written in P by Q form. Also today we have studied in detail that square root of all the prime numbers, they are irrational numbers. We have also studied different types of decimal expansion. So we have studied this using this flowchart. I'll show you this again. So if we have a terminating decimal expansion, then we say that it's a rational number. If we have non-terminating repeating decimal expansion, then we say that it's a rational number again. And for non-terminating, non-repeating decimal expansion, it's an irrational number. So children, we are done with this chapter, real numbers. Please revise at home, and wherever you have